So I decided to go with the graphical approach for this question. Now we want f of x to equal g of x and find the greatest number of distinct real solutions. By the way, because this is of order 5 and this one is of order 4, the most we could ever get would be 5 intersections. Because if you set them equal, you could then rearrange it to create a quintic, x to the 5. You cannot get more than 5. That's actually the fundamental law of fundamental theorem of algebra. Like a quadratic, you can't get more than 2 roots, for example, for the same sort of reason. Like it goes up and back down. You can get 2, but you just can't have it come back down again. So I'm looking for the situation, the different values of q and r, such that we're going to get 5 intersection points. Well, I'm going to sketch out f of x. Actually, it's not too bad to sketch out. It's going to go through 0, it's going to go through 1, and it's going to go through 2. And furthermore, it's going to have a double root at 0 and a double root at 1. It's a positive x to the 5, so it's going to come up from here and come back down and up again. And because it's a double root, it's going to come back down. I mean, I don't know exactly how far it's going to come down, but that's still a solid sketch of y equals f of x. Now let's think about y equals g of x. This has roots at q and r, both are positive. Q is less than r. And it's an x to the 4, but it's a minus x to the 4. That means it's going to come from minus infinity. It's going to hit the axis, come back down, go back up, and go back down again. That is what it's essentially going to look like. Now, the key thing to remember is that we need to guarantee there's the greatest number of distinct real solutions, 5, for any value of p. So, for example, you could say, well, maybe we could get this going on. But if I then make p smaller, then this would actually go inside here. So I have to guarantee it. And what that means is I'm gonna need to have one of them. I mean, I can't have them both here either. I can't have one of them here because like this will come back down. I'll hit it. Um, but then if I make it small enough, this bit here would sort of go on the inside. Also here I've got 1, 2. I've only got 3. And what that means is I'm going to have Q in this region here. I'm just going to realize that this goes to infinity more quickly than my green one. So I'm just going to modify it. So the green one could come in. And then like if it goes back down here, it's not necessarily going to go through 5 times. So it needs to, the second root then needs to be in this region. And you can see it comes up, goes back down, goes up. And then we will guarantee 1, 2, 3, 4, 5. It doesn't matter how we change p, make it smaller, make it bigger. We're always going to get these intersections. So we've got our first value has to be between 0 and 1. And our second value has to be between 1 and 2. And we already know that q is positive actually, so that means we just say that q is less than 1 and r is between 1 and 2. So just to say again, it's like if you had one here, it would come down, it would go back up, but then you wouldn't be able to, guarantee another load of solutions that we get 1, 2, 3. So it had to be, and also, sorry, we already knew that it had to be positive. If you put them both inside, then you can, it might come back down, but you can reduce p and then it wouldn't guarantee it. If you put one over here, then well, you're not going to get um, that sort of thing going on. Let me just, so it would have to, well, you'd have to put your second root somewhere. You'd have to turn around here. And again, you just wouldn't guarantee 5 solutions if you then reduced p enough. I'm hopefully that is convincing enough. I think it's quite hard, this question personally, but drawn a good sketch of the red curve, drawn a good sketch up here of the green curve, then thought about how we can guarantee 5 solutions, and it's got to be this one here.